Hello and welcome to lecture 9 of machine learning from data. In this video, we will be talking about logistic regression and gradient descent. So if you remember from the previous lecture, we talked about the linear signal, right? And then we categorized the problems that involve the linear signal into like 3 types. And we've already looked at 2 types. The first one was the classification problem, and then there was the regression problem. So today what we're looking at is the logistic regression problem. And just a quick reminder that these were the problems in which we were trying to look at the final probability outcomes. Right, so we are after like the probability values corresponding to a certain experiment or a certain observation. And the second part that we'll talk about is the gradient descent algorithm, the famous algorithm that is used to solve logistic regression type problems. Okay, so let's move on. And here, a quick recap of the linear signal. So we saw that this is what the linear signal is. Essentially, it's linear in the W's that we are to kind of estimate or find. And then this linear signal could be perceived as like or categorized into 3 parts, essentially. And the key takeaway of that previous lecture was that we wanted to get a smaller E of n, right? That was our goal in almost like every problem that we looked at. And in classification type problems, we saw that we can kind of improve on that and getting in a very small E of n by doing something that's known as feature construction, right? So we saw that example on the hand writing or recognition problem, right? Or classification problem, rather, I would say not recognition. We are not recognizing, we are classifying, right? So here we came up with 2 new features, and based on the domain that you're working in, you can come up with the features that you think are important for that problem, right? So for example, we came up with symmetry and intensity. You could have come up with something else depending on your knowledge of the problem. And as I said, it's usually done by looking at the previous, like the way that these similar type of problems have been solved, going into the domain and finding more about the problem itself and so on, right? But we saw that that feature construction played a very important role, especially in problems like the classification problems, because we had like a huge VC dimension, right, in the way the problem was initially given to us. And then we came up with a very good one eventually when we did feature construction. So that was about the classification problem. And of course, in terms of the algorithm, we looked at pocket algorithm. We also looked at how we can improve and make it more like efficient, like a good starting point. Where can we like get started and so on, right? So we looked at that. In fact, we also looked at something that's known as regression for classification eventually. And more like, to be precise, pocket algorithm is nothing but it can tolerate errors unlike the original PLA, right? So it is the original PLA, but then we are just like keeping track of our E in and keeping the best one. That's it. Finally, we came to regression type problems in which the outcome or my Y is essentially a real number, right? And this was like a really good algorithm. It's a one-step algorithm, although the efficiency of the algorithm depended on the data set itself, of course, but this was one step, and this was the pseudo-inverse algorithm, right? So we saw how the pseudo-inverse algorithm can be used to solve regression type problems. And then that pseudo-inverse algorithm was also useful for classification problems, especially like an input to the pocket algorithm, right? It provided a really good starting point. So that was from the previous lecture. And then let's move on to today's lecture, which is about logistic regression. So what is logistic regression? Well, in short, logistic regression is nothing but predicting probabilities, right? So that's what logistic regression does. We are not looking at real values. We are not looking at classifying things in one class or another, but rather we are looking at a probabilistic value, which obviously lies within this range of 0 to 1, because that's how we measure probability. A quick example is that let's say we have like a biological profile for a person here, and then for many patients, obviously, and biological profile is nothing but like their age, gender, blood sugar, and other stats and other things, and so on. Now, if this was a classification problem, what I'm really interested in is answering this question: will someone have a heart attack over the next year or not, based on like these inputs? So this is essentially my X, right? If this is a classification problem, essentially I have to answer yes or no, which is pretty straightforward. We have looked at that before as well. But if we are like solving a logistic regression problem, we are looking at the likelihood of heart attack, which makes more sense in problems that are related to medicine and these kind of scenarios. Because yes, this patient has a high probability of a heart attack, but we cannot like say for sure. And that's why we are looking at this logistic regression type problems. So the output of logistic regression is not a +1 or a -1. I mean, yes, looking at this profile, I can say that this person has a high chance of having a heart attack, but I cannot say for sure. I cannot say this is a +1 or a -1, right? So that is the basic logistic regression problem. And if you look at my input X, again, it will be formulated as a linear signal. So I can still use the linear signal as my input, but definitely I have to do something to it, to the linear signal, to get my probability values, right? So I don't want to have like a -1 or a +1, but rather I want to have like something like a 0.5 chances or a 0.3 chances or a 0.9 chances and so on, right? So basically I want a probability value using the linear signal itself. And in order to achieve that, what my logistic regression does is it transforms the linear signal. So I will be transforming it. So transform this linear signal using a sigmoid function, right? So transform using sigmoid, and I'm just going to talk about what sigmoid is to get these probability values, right? So that's how I'm going to get the probability values using the linear signal, of course. Okay, so reiterating what I said, in a logistic regression, I'm basically interested in predicting probability values. And there are certain problems in which we actually need to do that, right? So I'm interested in getting the probability values. Basically, my y is anywhere from 0 to 1, both included. Okay, and how does this work? Well, I have my linear signal, W transpose X, and I use the sigmoid function. So basically, I'm applying this function theta to my linear signal to get some outcome, right? Well, the question arises, why are we choosing this particular function over others? And I'm going to talk about that, but for now, just let's look at what this sigmoid actually does. So the range in which like my sigmoid function can like uh, go from is from 0 up to 1, right? And let's say this is my S, which is again W transpose X, and let's say this is like the 0 value for this, right? So let me just like draw a line 0. Okay, so this is an S-shaped function. Okay, I might not have drawn it like really well, but this looks like an S essentially. So it goes from 0 to 1. That's the range that it takes, right? So for example, if my my linear signal was exactly equal to 0, that means there is a 0.5 like probability of that thing happening, right? And so similarly, depending on the value of this, I can check where exactly the my outcome lies, right? Now there are a variety of functions we can choose from that have this sigmoid curve. We are choosing this particular one, which, let me write it down, looks something like this. And because this is mathematically convenient, first of all, and it has a lot of nice properties that I'm going to talk about. First of all, this is mathematically convenient to use this. And this has a lot of mathematical properties that make it really easy for us to formulate this problem to transform my linear signal into my probabilistic outcome. Okay, so what are some of the important properties of the sigmoid function? The very first one that we're looking at is, let's say this is my theta of s. By definition, this is the exponent of e to the s, 1 e to the s, which can also be written as 1 plus e to the minus s, right? Also, 1 over, like the inverse of this is 1 plus e to the minus s. So this is how it is a function of the linear, like the linear signal, and it is so conveniently written. A lot of things can be done here, as we shall see going forward, and which is why like this is the first choice. And in fact, like if I think about my research, I've used other functions as well, which kind of brings us to the discussion that There isn't a lot of, I would say, incremental gain in using those complex functions versus this one. And so that's why we use this, right? So there isn't a lot of gain that we kind of get while using other functions. And so this one is equally good, which is why we use it. Okay, so for example, the negative of this is 1 over 1 plus e to the s. And why I'm showing you this is because we use this relationship a lot. So of the negative s is nothing but, now this is, excuse me, this is 1 plus e to the s, which is nothing but, well, not this, 1 minus theta of s. Right, so these are some of the properties that we'll be using, and this will come in handy. That's why this function is used. And so going back to our logistic regression problem, what is the setup of my logistic regression problem? That is what I need to answer, having understood the sigmoid function. Okay, so yeah, like when we started talking about setup of the logistic regression problem, basically I'm looking at how to get the probability, right? So how will we collect the data, etc. So for example, going back to our example of patients, right? Oh, well, I have like these n number of patients, let's say, and I have like this input data for each one of them, right? So I have this, right? So ideally speaking, I should have the outcome values for each of these patients in terms of probability. For example, patient number one, in terms of like the data that I'll collect cannot have the probability of like whether this person had a heart attack or not, right? Because we don't know how to measure probability. The only thing that I'm going to observe, let me write it down, is of course some outcome, y1, which will tell me whether this person had a heart attack or not. Right? So again, what I'm observing, my data is going to be still yes or no. Again, similar for the second patient and so on. So this y here is still going to be a +1 or a -1 type of an outcome, right? Because I know whether this person got a heart attack or not. So the problems we've looked at until now, like the linear regression, the classification, the data was exactly the same as the classification problem, for example, right? Like, and for the regression also, like I had exact credit level for certain people, right? But here the challenge is that I don't have the exact, well, I'll write it down. I don't have the exact data, right? And whatever I have, whatever I have, like I have to like come up with a probability value using that, because I cannot measure or somehow observe probability, right? So I have to come up with some probability value using whatever I have. So basically it's important to understand that there is a challenge, right? Because we don't observe probability. We only observe this like yi being a +1 or a -1. Okay, so now, talking about the target function, obviously there exists a target function, which maybe in this case I'll write it as a ground truth. For example, if I have the data for myself, right, there is this underlying probability of whether I'll get a heart attack or not next year, right? I don't know that. It's just that I don't know that. So basically what I'm trying to say is that in this scenario, in this logistic regression problem setup, I have a probabilistic target function. And because of the probabilistic nature of the target function, it has some noise inherent in it, right? That's another way of putting it. It already has some noise in it. And this probabilistic nature is also telling us like how, like we need to map what we are observing with this like true probability or this ground truth or this probabilistic target function. So basically what we're trying to say is that the probability of observing, because you're going to observe that, right? You're going to observe a heart attack, yes or no. So the probability of observing a +1 given x is my target function, f of x, right? And then the probability of observing a -1 given x is, because this target function is representing this like probability of getting a +1, right? And so the probability of getting a -1 is obviously going to be 1 minus f of x, right? Because this is nothing but a probability value, right? But then we as like people who are trying to learn from this probabilistic target function, what is our goal? What is our hope? Well, our hope is to get an h of x, or maybe think of this as a g, get some hypotheses which is a function of x to be theta w transpose x, because this is what we are going to do, right? And our goal is that using this, we are able to learn, or we are able to come close to my f of x. That is my hope. That is my goal, right? So we must be able to construct a function such that we are able to approximate this probability value, right? In other words, we need to pick a final hypothesis g of x, which is obviously going to be one of those h of x's, right? Such that like I have like the weights that I choose ensure my E in of W is small or is minimized, right? For example, like I will definitely, because my entire machine learning problem is like based on getting a very small E in based on certain weights that I will pick for my linear signal, right? So I really want to minimize this first of all. If you remember in classification, we use this like pick weight such that the fraction of misclassified points is minimized, right? In regression, it was the squared error. So obviously we have to come up with a good definition of E in, then only we'll arrive at some G of X, right? So let's see what the process here is. So basically the process here is, of course, I don't know my f of x, so I'm saying the probability of getting +1 given x will be very close to h of x, which I will come up with based on the weights that I'll pick, right? And so the probability of getting a -1 given x is very close to 1 minus h of x. Okay, so having said that, now going back to the observation for the data point, let's say xn, right? So if we are observing some x of n, for example, I observe x of n, and what I get is my y of n, let's say it was +1, right? So then I will say, based on this like information that I have, then I'll say my h of x is almost equal to 1, right? And similarly, when I observe some other x of n such that my y of n is -1, then I will be able to say that my h of x of n is almost equal to 0, right? Or maybe, yeah, that's -1. And then, because this is something that I'm using to approximate a probability value, right? So, as I said, like this h of x of n should approximate the probability value. And so how can I do that? Well, I will get h x of n using these two equations here, right? What I'm going to get is like this is almost equal to half of 1 plus y of n, right? And of course, we have to approximate in sample error, right? So the way I'll write my in sample error is, let me go to the next slide. The way I'll write my in sample error for whatever h I finally picked up is 1 over n. N is from 1 up to n, h xn minus half of 1 plus yn. And this entire thing, well, I already had this, right? So it doesn't make a difference, squared. Okay, so we can call this squared logistic regression error, just like we said for our linear regression problem. But there is one problem here. The problem is that we cannot use it. That's bad news for us. We cannot use this, at least in this current form, because number one, well, this is mathematically inconvenient, especially because we will be minimizing my in-sample error. Remember, the goal is not like I'm not done here. I have to go and minimize this in-sample error. And mathematically speaking, it is inconvenient to minimize this. Okay, that's the first one. The second is, if we look at h of x here, all I'm doing here, because this was an approximation for my f of x, which was nothing but a probability, right? But if you look at it here, what I'm doing is like just looking at my y's, and based on my y's, I'm simply getting a 0 and a 1 for them, right? And then simply calculating their average somehow and, getting that value out there. So where is the probability that we talked about? Where is the probability approximation? Or in short, there is no probability approximation here, right? So we're simply trying to make my h of x of n 0 or 1. And so there has to be a better way to represent this, the in-sample error, and which has to be consistent with the probability values that we are trying to approximate, right? So let's look at that in the next video.